Okay, so now that we've seen what is Schumacher theorem, I want to drive you through the different elements that can help us build the tool to prove this Schumacher theorem. So first, there is a typical subspace that we talked about. We say that there is a row A, and so there is a rate of compression alpha, and that inside of it should have the uncertainty h of A. And so typical subspace, let's introduce more formally what it is. If we let row A, believing into the density matrix of A, and row A, write and have the sum of x of lambda x vx being the spectral decomposition. Then we have row x or m, which is equal to the sum of x1 to xn of lambda x1 to lambda xn of vx1 to vxn of vx1 to vxn. Here just extended to x1 to xn instead of just 1x. But so yeah, at the beginning we can just see this as if we had a qubit that goes out of our stuff. Let's say the qubit have a probability lambda 0 of being 0, and lambda 1 being a probability of 0.2 of being 1. So yeah, our qubit is a probability lambda 0 and lambda 1. And so here is just we have one qubit, and so here just a generalization about it. If we have n qubits, then suppose we have n equal 10 qubits, then this formula tells us that if the output is 0 0 0 0 0 5 6 7 8 9 10, we have 8 0 and 2 1s. Yeah, we have 8 0 and 2 1s. 2 3 4 5 6 7 8 9 10. Then we have a probability of, because it's the probability of having 0, it's 0.8, so it's 0.8 divided by 0.8 multiplied by 8, sorry, because we have 8 qubits, plus 0.2 multiplied to the power of 2, and so it's decimal 67%. And so yeah, just to illustrate what it means, and yeah, this is exactly the form of identically distributed independent source, as we see are identically distributed. There is no they're the same states that are generated, but they're so independent where the source does not imply the first qubit will not be generated, will not be have an application of the second one that would be generated. And so yeah, that's the Schumacher genius. If we measure those qubits, we will obtain the same distribution called statistic as if we have launched 10 times a piece that is where we can that is strict. So the contemporary just became a problem of classical prophecy that are identical, distributed, and independent. And so that's the first step, to go in a way to those contemporary, to this probability classical independent and identically distributed problem. And the second step will be to see what we can have about, which is well, maybe I can just first say this, what I said here, if we measure in the eigenbasis, then vx1 to vxn, then the spot distribution will be identically distributed and independence distribution. So px equal px1 plus pxn, which is x1 by lambda x1 by lambda xn, which is our 0.8 and 0.2 in our example of the tricking case. So yeah, so let's remember the first step. After the second step is like to see what we can about it. Like if we think back to classical typicality, we can define the atypical strings, the epsilon typical strings, such as we have t and epsilon, which is equal to x1 to xn, to 2 to the power of minus n ha of epsilon, to inferior to lambda x1 xn, which is inferior to 2 to the minus epsilon of 2 to the power of n of ha minus epsilon. And so basically this just tells us that like I suggest you to not panic because this equation is easy, like just telling us that our source is entropy of an element that in our case like is less or more 67%. Will be like I didn't make the calculation, maybe not this, but yeah, let's say 67%. The entropy of an element will be equal to this, HA will be equal to 0.77. And if we take like n equal 1000 qubits, it's just a typical subspace of our stuff, where we have most of the time like we will have like 800 qubits being 0 and 200 qubits being 1, and that's the typical subspace, no matter the order about them. And yeah, just that's it. And so on the channel I can go into this club if like it's the probability will be like 2 minus 0.067 because of the probability. So yeah, so that the typical chain is like 100, 0, 201, and untypical one that we will ignore is like 1000 time with only 1, or like 1000 time with only 0. And yeah, so that's what we got about it. And to illustrate like the relation to epsilon typical subspace. So yeah, now I will drive you like when we have selected like those winning, in a way, classical winning sequences that are in occurrence 800, 0, 201. We can create a subspace, vector subspace that we can call Vn Vn epsilon, which generates Vx1 to Vxn with x1 xn being into Tn epsilon being into A over n. So yeah, that's it. Like from the winning chain, we can like put them here and generate our space or subspace that is composed of the quantum typical states. So that are subtypical state space. And so after like we can after then define the projector onto the subspace. Um, that can be like rated as Pn epsilon, which is equal to the sum of x1 to xn to going into Tn epsilon, such that we have the x1 to the x2 to the xn, then here x1, x2 to xn, and yeah, just like to in a way to isolate mathematically this stuff um, with our subtypical space, like how to isolate it. We just derive like a projector, and it just like saying as a it just like arrive as a if the quantum state correspond to a combination probable like 800 0 and 201, then there will be no unification. But like if the state is like weird, then there will be a problem about it, and it will be equal to 0. Like the 1000 0 will be equal to 0. We will ignore them. So yeah, that's it. And so what we can say after is like as P and epsilon is a projector, and epsilon identity minus projector and epsilons forms a POVM, and by spectral decomposition, the trace of rho x or n of the projector and epsilon is equal to the sum of x1 to xn, leading to t and epsilon going from lambda x1 to lambda xn. So basically saying that the being like with this formula trace, like by making the sum of the probability of all of our chains of sum of the probability of all of chains of like 0 and 1, like we have 0.00 n time plus 0.211 m times, then it just tells that we can have as long as the chain is really big, the more the chain will be big, the more it will convert like the asymptotic rate of compression that we was talking about. Yeah, it will reach the 100%, and that's why it's cool. Like about it, like we reduce the space and still can have with this compression literally the same as before, but with less qubits. So basically, in our case, we just went to the 1000 to the 670 qubits, and so yeah, the probability is your is just, and so we just use less qubits, and we can destroy all the rest of it. So by eliminating the unuseful dimension, you just take 100% of the quantum state and this entanglement stuff, exactly as they were, but we reduce like the stockage by less from like 20%. Like you go from 1000 to 670. So yeah, the quantum compression theorem is like developed like using this result we have developed in classical immersion internally. We like yeah. So yeah, basically thanks to this we can derive some proposition, and when we can deduce from this is that like if we let like row A living into the state of A and moving into A, epsilon strictly is equal to 0, then we have like 1 no matter epsilon being strictly equal to 0, the limit of n going to close affinity of the trace of ray A, where n of the projector of n epsilon is equal to 1. So yeah, basically like even by compressing like as n grows like row A, because A is mostly contained in V and in VMC, like in not in the projector subspace, but in the E typical subspace, in the epsilon typical subspace, yeah, basically we have this, and so it's like our one. So with 670 qubits, we can like do the same, and the dimension of Vn epsilon is just equal to the typical subspace, like being like 2 to the one of NHA plus epsilon. And yeah, with the dimension of the typical subspace, it can be much smaller than the dimension of X or N. Like basically, we just like economize 272 to the power of 228 qubits, like going from this to this. Well, I didn't take the exact calculation. I think that's this, and so yeah, we just economized a lot, and that's really cool, and yeah, basically um, we win about it. Like we just win 280 qubits, 670, 228 qubits, and yeah. So yeah, we can go to a percentage from our 100%, and that's cool because well, you see here what is the genius of Shannon. He just takes the Schumacher genius, like he just takes the Shannon theorem, like which says like his intuition was like just to give you an intuition of how to discover something. He just say like I just if we take a series that produces like false probabilities like 80% A and 20% B, the law of big numbers will make at the end that this majority of possible texts will never appear. As we see, like it will be like for 1000 will be 800%, 800 A and 200 B, for example, typical um, in the typical subspace that could be a typical sequence into it. And so the genius is just to say okay, by diagonalizing the density matrix, diagonalize like the density matrix, then the eigenvalues will behave exactly uh, exactly as a classical probability, like classical proba of Shannon. So he just like in a way just transpose the Shannon statistical filter into the quantum Hilbert space from quantum physics, and the comparison uh, theorem is born.